Okay, so let's talk about the second law of thermodynamics. There are actually four laws: the first, the second, the third, and believe it or not, there is a zeroth law of thermodynamics. Go look it up if you have questions about that, because it does sound weird. But we're just going to talk about the second law because it is by far the most important of the four. So, the second law of thermodynamics says this: there's actually several perspectives. The first perspective to understand the second law of thermodynamics from is from the perspective we've been talking about already, which is heat. The second law says heat will flow spontaneously from high to low or hot to cold. And that word spontaneously, we've talked about before, it means automatically. Specifically, in this case, it means there is no input of energy necessary to get heat to flow from hot to cold. This should be obvious when you put a hot object next to a cold object, or when you put that cup of coffee out on the table, when you put the cold cup of soda out on the table. Heat naturally will transfer from the warmer area to the colder area without an input of energy, without any trigger. It's nobody's job to make that happen. It just happens, similar to the downhill flow of water over a waterfall. Now, the important thing to understand about the second law, and this is really the second perspective to understand the second law from, is that the second law is not only about heat. This is just what it says about heat specifically. If we consider all energy, we realize that the second law applies to all forms of energy. That's why it is so important. It's not just about heat. And so when we look at all forms of energy, what the second law says about energy in general is that energy spreads out. That's what happens to energy all the time. So when we consider and back up consider like all forms of energy and sort of back up from the picture, the second law, when we talk about energy spreading out, explains things like not only heat moving from hot to cold, but when we talked about electricity, we said electrons move from negative to positive. Well, this is energy is just spreading out. If you think about it, electrons, electrical energy is concentrated on the negative terminal because there's an excess of electrons. There's a deficiency of electrons at the positive terminal. And so these electrons are simply trying to spread out, and they do that naturally, automatically. It's similar to the concept of diffusion in biology, which is a movement of particles from an area of high concentration to low concentration. So you can apply that same concept to sort of the second law: diffusion of energy, high concentration of energy, low concentration of energy. It also governs things like light. When you put a lamp in the corner of your room, it doesn't only light up this area, it'll light up your entire room because energy spreads out. As a matter of fact, there is only one single source of light in our entire solar system, one single source of energy, and that is the sun. The reason there's only one is because its energy spreads out naturally. When you throw a rock into a pond, the ripples flow outward because that energy is trying to spread out. And in class, when I face away from you, you can still hear my voice. When I am not facing you, because the sound energy from my voice, like in this picture, seems to or wants to spread out. So the second law of thermodynamics talks about a lot of things. It governs all energy. All energy types simply want to spread out. The third way to understand the second law is to talk about entropy. Now, we first need to understand what entropy is. Entropy is defined as the amount of disorder in a system, or the amount of chaos in a system. And that's important to understand because many times it's confused to be the amount of order in a system. It's not the amount of order, it's the amount of disorder. Like, how much chaos is in a system? Ask yourself right now, what is the level of entropy of your bedroom? If I'm being honest with you, the level of entropy of my bedroom is pretty high. I'm not very good at keeping it organized. And so that's what entropy is. And when we get to the second law tells us that a system, all systems, naturally or spontaneously move toward greater disorder. In other words, the entropy of the entire universe tends to increase, and this happens naturally. This picture down here on the bottom of the screen is a great example of what we're talking about. Imagine you toss a pile of bricks off of a truck or a building or whatever. Which pile of bricks would you more likely produce? Well, obviously this one is the most likely because disorder is the most probable scenario. That's because of the second law. Systems naturally tend toward greater disorder. Could this pile happen on the left? Yes, it could, but it's extremely unlikely. In a similar way, think about your bedroom. If you clean your room up over a 1 to 2 week period, or maybe even a shorter amount of time, if you don't do anything, the entropy level of your bedroom tends to increase and increase and increase. In other words, your room tends to get more and more messy and disordered. And so when we think about this disorder spontaneously increasing, another question arises, which is, can we decrease that entropy? Can a system become less disordered? Or another way to say it is, can we reorder the system? Can systems become more ordered? If the second law says systems tend toward greater disorder, can we move a system away from greater disorder? A similar question is something we've talked about before. In regard to this water pump, we know water flows downhill spontaneously. The question is, can we get water to flow uphill? And when we think about it in this way, the answer is yes, we can. But I think you can probably understand that that is not going to happen naturally. And the same is true of energy. So, can entropy decrease? Yes. But in order to decrease entropy, to increase order in the system, that takes work. It takes an input of energy. And this is what we talked about in the battery. Electrons naturally or spontaneously flow toward the low potential or positive terminal. But when they get there, the battery, through a chemical reaction, does work on the electrons to bring them back to the negative side, which decreases the entropy. It reorders the system. It reconcentrates the energy so that they can flow downhill again. So this is important to understand that the second law says energy naturally tends to increase. If you want to decrease entropy of the system, it takes work. Similar to the bedroom, to your bedroom. If you want to clean up your room to decrease its level of entropy, you can certainly do that, but it's not going to happen naturally, like snapping your fingers like Mary Poppins. You have to do some work and clean it up. So you might be wondering right now, what does this entropy thing have to do with what we were talking about earlier, which is heat? Well, what it has to do with heat is that the greater vibration of particles, we talked about particles vibrating, means they have greater disorder. And so when we say that the entropy of the universe naturally increases, what we're saying about heat is that molecules naturally tend to absorb more vibrational energy so that they vibrate more. In other words, as molecules or as objects increase their temperature, it increases the chaotic vibration of their molecules. And I want you to look at this GIF that you see on the bottom of the screen. There's a couple of things that I want you to notice as it progresses. The first thing is probably you notice that the colors change, and the colors are representative of temperatures. And the temperature is also representative of how fast the molecules are vibrating. So at the beginning, on the left side, we have these highly vibrating red molecules. That is to represent a warmer part. And so the second law says that entropy tends to increase. These molecules over here on the right, which are not vibrating as much, they are more ordered because their temperature is lower. On the left, these molecules are less ordered because their temperature is higher. And so the second law says entropy naturally tends to increase, and that is what happens to the molecules on the right side. They are absorbing energy from the molecules on the left, naturally increasing their level of entropy. And then another question that can a couple of questions that can follow this is, what happens to the temperature of these objects as they exchange heat? Well, not surprisingly, what happens is that the warmer object gets cooler, which is indicated by the change of color in these molecules on both the left and right side, and the cooler one gets warmer, right? The coffee temperature will decrease, the temperature of the air, at least right around the cup, will increase. As the heat flows from the air into the drink, the temperature of the air surrounding it will decrease because it's losing heat. And again, that's the key to all of this, is that we have to understand all of this is happening because of the second law of thermodynamics, which says that heat flows from hot to cold, hot to cold, hot to cold. And that causes temperatures to change, obviously, because one is losing heat, one is gaining heat. The last question about this is, when does this heat flow stop? Probably not surprisingly, you can understand that the heat flow stops when the temperatures of both objects are equal. And this condition is called thermal equilibrium. Obviously, when the temperature of the warm object decreases, the temperature of the cooler object increases. They're going to reach a constant temperature, the same temperature. And as we stated before, if they have the same temperature, there can be no more exchange of heat. So thermal equilibrium is a specific condition whereby temperatures have, or two objects rather, have reached the same temperature and therefore they no longer exchange heat between them. That's what thermal equilibrium is called.